In this lesson, we'll continue practicing what we learned about the Wilcoxon sign rank test. This time the question reads, the accidental incorporation of polybrominated biphenyl compounds into high-protein dairy pellets led to the contamination of dairy herds in some Midwestern states. A study is conducted to determine whether cooking reduces the PBB levels in meat from contaminated animals. The experiment is conducted by measuring PBB level in raw roast sirloin tip, which is found in the X column, cooking the roast, and then measuring the PBB level to the cooked meat, which we find in the Y column. That data is shown on your screen. We need to conclude that cooking effectively reduces the PBB level. The first thing that we want to do is write down our hypothesis, but before we do that, this requires that we use a non-parametric test because we're not told that the data is normally distributed. And we use the Wilcoxon sign test because it's better than our alternative being the sign test. Also, the information here is dependent. So we see a before and after effect for each observation that has been collected. We'll start with the null hypothesis. And for this, I'll say that the median levels, remember with these non-parametric tests, such as the Wilcoxon sign rank test, we use the median, and that's denoted with this tilde. So the median here is greater or equal to the median of the raw. And the opposite is true for the alternative. For the alternative, we expect these levels to be greater than after it's cooked. Now we have to find the difference between the before and after and extend our table. So I'll be subtracting 0.15 from 0.19, essentially all the values in this column minus those values. Extending my table, I'll call this differences, or D for short. We have 0.04, 0.10, and the rest of the values should be what you see. Next, we have to rank these from smallest to largest. And when you rank, make sure that you take the absolute of the number. In other words, this negative 0.01 is actually 0.01, and the same applies here. It's 0.02. We won't be ranking 0. So this is the smallest number. I'll give it a rank of 1. Then comes 0.02. That gets a rank of 2. Here we have 3, 4, 5, 6, 7, 8, and 9. Now, even though we took the absolute of these values, when you find the rank, you also want to place the numbers that were negative as negative values. Another reason why it's important to keep note of these negative values is because when we calculate the test statistic, which is shown right here, we need a value of t, and that represents all the positive ranks. So 4 plus 8 plus 5 plus 9, 6, 7, and 3 gives us a t value that is equal to 42. Our n value represents the number of ranks, which happens to be 9. There are 9 ranks in total, minus, of course, this that was never ranked. Now we can go ahead and calculate z. Z is equal to 42 minus 9, bracket 10, 9 plus 1 is 10, divided by 4, over the square root of all of this mess. So we have 9, bracket 10, bracket 19, over 24. Putting this all into your calculator should give you a value that's equal to 2.31. That will be our Z score, 2.31. We need to find the probability that Z is greater than 2.31. You can locate this in a table. Here's the table shown on your screen. So I'll take 1 minus the probability of Z being greater than 2.31. This ultimately depends on the table and how the values are recorded. Subtracting 1 minus this value, which is 0.9896, we end up with 0.0104. This value is less than 0.05. And because of that, we have to reject the null hypothesis. If we reject the null hypothesis, that means we have sufficient evidence to conclude otherwise. We have sufficient evidence to say that the medians of the raw meat is greater than the medians of the cooked meat. So cooking it actually reduces the levels of PBB. There you have it. Another example on the Wilcoxon signed rank test for dependent samples.